We have a minute.
Yeah, it takes a minute to set it up.
Morning, folks.
Morning.
I was
Good
just an
afternoon.
audio test.
Oh
yeah, good afternoon.
Okay, we're now live on YouTube. We just begin the recording as well. Okay. For myself. All right, I think we are all set to begin the second day of the 12th Gaia Science Alerts workshop and the first ORP time domain astronomy workshop. So today we have a long list of very interesting talks, and I give floor to Paweł Zieliński, who will be chairing today.
Okay, hello everyone. Good afternoon. It's a pleasure for me to be a chair for the both session today. So the first speaker is Gabor Marton, who will tell us about the automatic eyeballing of Gaia alerts. So Gabor, you have 15 minutes, and let's start. 15 minutes with questions.
Yeah. Okay, I will try to fit in.
The floor is yours.
Okay, thank you. So yeah, I'm a little bit of echo from the Konkoly Observatory, Budapest, and this project I'd like to present today is something I already presented a few times, but of course there are always updates and news. So the next slide, yeah. Very briefly, I want to talk about these photometric science alerts of Gaia. Of course, I think everyone knows quite a lot of things about this. A few words about the eyeballing and the voting system, the methods and the data, what machine learning approaches we use and tried, what are the images and the parameters in this project that we analyzed. I will show a few results, and there will be a very short summary of the current status and the future aspects. So yeah, of course, the alerts, as you know, start with the data collected by the Space Telescope, and there is an alert pipe analyzing this incoming data, and it gives you a long list of alert candidates, which, as far as I remember, a few thousand alerts a day, but since not everything is perfect, these are filtered for artifacts and other possible errors. And after the filtering, there are a few tens of candidates after each run, which is each day or probably a day, one or two more runs can be eyeballed. But yeah, so these candidates are eyeballed by humans. And this is what this wet neural network means. This is the brain of the team, which decides which sources will be published. And of course, you have quite a lot of things to consider when you vote. These are the images which are looked at, describing the light curves, so the brightness changes of the sources, the environments, and also parameters like the goodness of fit. So yeah, these all have to be looked at to decide which alerts are going to be published. And the way the team works is they are using a voting system. So if the alert is really good and it seems to be really interesting, it gets a definite yes, which is a score of 1. If it's really a no-go, then it gets a score of -1. And in between, there are half scores. And of course, if we don't know or the given voter doesn't know, if it's a really interesting candidate, they can give a score of 0. But the thing is that the total score must be 2 or higher to be published. And as you can see from these diagrams, these are names from the last 30 days and from the beginning of the alerts with the number of votes each individual gave during these times. And as you can see, there are quite a few people who, yeah, from time to time they vote. I didn't vote in the last 30 days, sorry for that. But there are a few people who vote on a regular basis, and it takes a lot of time for this core team. And that's why the idea came up that publishing should be somehow automated. So since machine learning is working quite well in almost every aspect of our life already, it was an idea to use these machine learning algorithms. There are many ways to use them. There are supervised, unsupervised, there are deep learning algorithms. Based on the input data, they have a different way of working. So you can use numbers as an input data, or you can use images, which are, of course, for the computer are numbers, but in a different style. You can use random forests, support vector machines, whatever. There are quite a few methods to be tried and which we applied. And of course, the ultimate question is that can the machine differentiate between published and unpublished alerts as humans do? So on the left image, you see an alert which was published. You see the outlier quite clearly. That's the red dot at the top of the image. And on the right, you see a light curve, which has, of course, a quite big variation. And there are outliers, but they don't seem to be very significant. So for this image processing and to make decisions based on images, we use the PyTorch code, which is a deep learning framework, and it has a Python implementation. And what we use are those images are already showed 4 images describing the light curve and or showing the light curve and the environment and other parameters. Each image, so these are 4 images, but each image has 4 plots. So in total there are 16 plots, and if you include the total images, there could be used 20 images to classify. And of course there are 4 types of the alert detectors. So in total this makes like 80 different possibilities to classify an alert. Okay. If you are using numbers, like for the random forest classifier, there are many parameters that you can calculate and that can describe the source or the environment. Here I listed a few that we used as environmental parameters. They include a few of the light curve parameters as well, like the historic average or the amplitude, but it also includes these really environmental numbers, like the number of DR2 sources within a given radius, or the offset to the brightest neighbor, and so on. So in total, in this exercise, we had 19 features. And from the light curve, you can calculate also many other features. There is a Python package I used, it is called the feeds, and it really has a big number of features that can be calculated. We used 34 of these features. And of course, these can be combined with the environmental parameters. And I'm already at the results because I don't think that the technicalities are too important or too interesting for you. But here are a few examples of results. So if we use this light curve image with these 4 plots included, and we want to classify the alerts based on this image with the PyTorch, you can see that the accuracy for the delta mark kind of alerts is a bit above 90%. It's a bit lower for mean RMS, above 80. For the skew von Neumann, it's around 75%, and for the new sources, it's again above 90, 92, if I remember. But if you use the environmental images to classify the same sources, then the accuracy drops a bit, a few percent, like 5–6% for all kind of source alerts. If we use these parameters calculated from the environment and from the light curve, again, you can see that results are not so bad, but didn't work in the same way for all kind of alerts. But if you combine the environment and the light curve parameters, then for example, for the data kind of alerts, it goes up to 97–98%. And it's also quite good for mean RMS and skew von Neumann. Of course, for the new sources, you don't have a light curve, so you cannot really calculate light curve parameters and combine them with the environmental parameters. That's why for the new sources, I don't have a bar. So for each classification, the algorithm spits out a probability, and this probability tells you if the source should be published or it should remain unpublished. And based on the threshold that you want to apply, the false positive rates and the false negative rates change. So the false positive means that we are more complete, but we add quite a lot of garbage, while the false negative means that we are quite clear, but not so complete. And you somehow need to balance between these numbers. And that's a topic where a lot of discussion is being made. And at the moment, we have some preliminary ideas. Of course, this can change, and I'm sure will change with time. But for example, if for the data kind of alerts, we combine the environmental random forest classification, now the environmental plus light curve random forest classification with the image-based classification, and we set a threshold of 0.6. So sources published if the average probability of the alert is above 0.6. It means that for the published alerts, we have a 96% accuracy. For the unpublished, it is 98.7. For the mean RMS, you can see it's 94.7 for the published and 97.2 for the unpublished. For new sources, 94.3 and 87. And for the skew von Neumann, it is quite good. For the published ones, it's 98.1. For the unpublished, it's 84.6. So it means that we can calculate for these thresholds. If we apply these thresholds, we can calculate how many spurious alerts we would add per run. So these are the alerts that won't be published with the current human voting system, but the machine would add them, and we can calculate how many, let's say, real sources we lose per run on average. And as you can see, in total, with this setup, we would add one spurious source in every 3 runs, and we would lose one real alert in every second run. But these numbers, as I said, are compared to the human eyeballing, which is also imperfect. It depends on the mood of people, for example. So yeah, it doesn't mean actually these numbers that the alerts will be better or worse. So this is my last slide. I hope I'm on time. The current status and the near future plans. So the models are finalized, let's say. They are finalized for the implementation. It doesn't mean that in the near future we won't update the training samples, adding more alerts from the most recent runs, but it was necessary at some point to freeze these so the code can be implemented, and it was already implemented. It is up and running, although the results are not public yet. We are collecting the new results, and we will analyze them, and based on those, we will decide if these thresholds needs to be modified, how we need to combine different probabilities from the different classifiers. So this is the validation which is ongoing, and there are discussions going on. What we want to actually achieve? Do we want to have a more complete sample to be published, or do we want to go for purity? Of course, to do this, to decide, we will have a look at the other alert systems. But we are quite close to the finish line, which is good because we need to be close to the finish line. That's all.
Thank you very much, Gabor. Okay, it's time for questions. If you have any question, please raise your hand on Zoom or use a chat on Zoom. It's valid also for people in this room. It will be easier to everybody to see the hands. And Chris Rybicki raised his hand. So, Chris.
Yeah, thank you. Hi, Gabor. Nice talk. I have a question. If you did any check of how the classifier behaves in the context of different classes of objects, I mean, if it maybe works better for supernovae or for words for microlensing or whatever like this, do you have any clue?
No, we didn't check the actual stellar classification. We just checked for these alert detector types. So no, I have no idea. But for the new sources, we know that they are mostly supernovae, for example. So in these terms, they are comparable. But yeah, for the skew von Neumann, let's say I don't know if microlensing or slowly rising YSOs are better classified. I have no idea.
Okay, thanks.
Simon, if you have a quick question and simple one.
It's a complicated one. It's a simple question. But I'm changing the stream because I would rather work the way that ZTF work, and maybe Ashish can talk to this, where we have a contaminated stream, but we have a probability of the trustworthiness or the real bogus score of an event, but we publish more stuff. But the other approach is to try and keep purity as high as possible. So I'd really like to know how people would feel about those two different extreme modes of operation.
I think it's a good point for a broader discussion. I suggest we move it on Slack.
I'll put it in Slack. I'll put the same question in Slack.
Please. Yeah,
please put it. Yeah. Okay.
Yeah, and I think on that point, I would also like
Yeah.
to comment about the different binary classifiers where we carry multiple probabilities or confidences for the same object from different classifiers.
Okay, thank you, Ashish. Thanks, Gabor, again. The next speaker is Eleonora Fiorellino from Concolio Observatory as well. Eleonora, can you share your presentation?
Sure, I'm going to. Can you see my screen? The presentation will be about, we see your screen in full screen mode as well. So it will be about the new XOR candidate from Gaia Alerts. Can you hear me? Eleonora, please. Okay, so hello to everybody. My name is Eleonora Fiorellino. I'm a fellow researcher at the Concolio Observatory, and I'd like to thank the organizer to give me and my group the possibility to show you some nice results we've got on this new XOR candidate, Gaia 20 EAE. Here you can see the list of authors of a project led by Fernando Cruz de Miera. So before starting, before talking about the source, I'd like to introduce you a little bit the star formation scenario. Everything starts with the prestellar phase where giant molecular clouds fragment into stellar starless cores, which are those roundish objects composed by dust and gas, which can eventually collapse if their self-gravitation is larger than the thermal pressure. So right after the collapse, we've got the protostellar phase, and for the first time, we are able to observe young stellar objects, which are composed by the central objects, so the forming star, which is embedded on an envelope. And from this envelope, through a circumstellar disk, according to the magnetospheric accretion model, the material is supposed to flow onto the central objects and increase the mass of the star. We can study this also by looking at the spectral energy distribution you can see here. In the last step, we are able to discriminate between the central objects and the infrared excess, so the activity of the disk, which traces accretion. Right after the star fall in the priming sequence phase, at this moment, the accretion is not the main contribution to the bolometric luminosity anymore, but is still present, and it diminishing with time until in the last step, the temperature reaches 10 to the 7 Kelvin, the helium burning stars, and we have our star in the main sequence. During all this process, we can describe the class of the objects by looking at the slope of the spectral energy distribution between about 3-4 microns and 24. But this scenario has some problem. One of these is the so-called luminosity problem. This is the problem according to which the observations we have of young stellar objects show a luminosity too low by as much as 1 order of magnitude with respect to what expected by models. So in order to solve this problem, several models were developed, and one of them seems to be successful. And this, according to this, the accretion is not a steady process, so the material doesn't flow steadily from the envelope to the central star, but this happens by bursts. And here you can see a model by Hartmann, but there are a lot of them, according to which the mass accretion rate, so the amount of material in stellar masses per year which accrete onto the central object, can have bursts, and in particular, I want to look at the so-called Feuer burst, whose accretion rate can reach 10 to the -4 solar masses per year, which is a lot, and XOR-like burst. So in the first case, Feuer-like outbursts are last a long time, about centuries. In the second case, they are shorter, less intense, about 10 to the -6 solar masses per year, but more frequent. And in general, this kind of outbursts are quite rare. So the occurrence of eruptive bursts is estimated to be once every 10 to the 4 years. But to see whether this scenario is confirmed or not, we need way more observation of these objects. And up to now, only 50 eruptive sources are known. So how can we determine, how can we look for other eruptive sources? The sources are variable, so they experience variability. And here you can see that the variability of young stellar objects in general can be due to different kinds of phenomena. And among these, we have X-LUP outbursts and Feuer outbursts, which are the sources we are interested to. So the idea is that the amplitude of the variability of young stars is larger than 2 magnitude. Maybe we are looking at those kind of objects. And this is the idea we have when we started monitoring the Gaia Photometric Science Alerts program that Gabor already explained. And in this way, we found several sources, among which Gaia 20 EAE. And I'm gonna show you why we think it's new XOR. So this is what we knew about Gaia 20 EAE before starting our work. So this source lays on Aquila constellation close to the galactic plane, and a brightening on the near infrared was already reported by Akin's 2020. When the Gaia alert was triggered in J-band, determined by an amplitude in magnitude of 4.6 magnitude, which is a lot. So according to the Gaia distance, this source is at about 3 kiloparsec. But as I said before, it lays on Aquila constellation. So it doesn't belong to the Aquila star forming region, which is at about 400 parsec. But still, looking at the catalog of candidate YSO by Robitaille et al. 2008, this source is labeled as a candidate YSO, and also other sources, 3 other sources with similar distances of about 3 kiloparsec are listed in this catalog. So our guess is that maybe there is another star forming region behind Aquila star forming region where several new YSOs that Gaia will help us to analyze better lays, and this is one of them. Okay, so let's look at the light curves. We collected all the data that were available, and we also observed with other instruments, and we suddenly notices that there are the short-term bursts typical of XORs. So these enable us to continuing our investigation, thinking that, yes, we were looking to something really, really interesting. And we made further observation, in particular between 2020 and 2021. Here you can see all the data we collected. And in particular, I wanted to show you that for example, this is an observation we made on June 2020, and here you can see the magnitude of the light curve. And then on April, when the sources was dimmer, actually you see a dim source. It is just nice. So with all these photometry, we build the spectral energy distribution. And we were able, from the creation spectral energy distribution you can see here in orange, we were able to estimate the spectral index that characterized the source, finding a source of minus 0.33, which is compatible with a class 2 young stellar object. So the first step of the permanent sequence stage of the star formation. And we also compared the observed SED with the median of all the SED of classical Titario of class 2 young stars in the Taurus region. And still, so this shows us that this source can be treated as a young star. And from the basically the stellar contribution, we were able to determine the extinction, which is about 5 magnitude, and the effective temperature of the star, which corresponds to 4,300 Kelvin, suggesting a low mass, late type star, so a spectral type of K5. We were also able to determine the stellar parameter of this source, and still you can see that those are typical of class 2 objects. But this is, so one of the most important thing for these objects, as I explained before, is that they are creating, and they're creating a lot in bursts. So we need to see if they were accreting, and we've done it by spectroscopy. So we made several spectroscopic follow-up, and we compare our results with the one of the X-Loopy star, which is the prototype of XR-like objects. So here you can see the near-infrared spectra in JHK band of our data in black and orange, compared to the X-Loopy ones in blue, and you can see that there is agreement between the two spectra. Also, the spectroscopic features typical of XR type are shown in here. So you can see that we see hydrogen 1, Russian beta, and bracket gamma, which traces accretion. So this series is accreting, but also the CO banded in emission, which still is suggesting us that we are looking at an XR-like star. We wanted to quantize the accretion, and to do this, we used the empirical relationships relations by Alcala 2017, which link the line luminosity to the accretion luminosity. And through this, we were able to compute the mass accretion rate. So here you can see list of the lines we investigated in the near infrared and in the visible as well. So here you can see the H alpha line and the accretion luminosity and the mass accretion rate we derived. We find a value of about 5 times 10 to the 7 solar masses per year, that for a class 2 object, so about 10 to the 6 year old, is supposed to be exactly in agreement with what we expect of an XR outburst. So again, this convinces us that we are looking at an XR-like star. So I'm leave you with take-home messages summarizing what we've done. Gaia 20 EAE lays in a region of the sky behind Aquila forming region, close to the galactic plane, and eventually it belongs on a new star-forming region because it's surrounded by other candidate YSOs at about 3 kiloparsec. We analyze the light curves, we show variability typical of active sources. We also investigated the near-infrared and visible spectra, finding the spectroscopic features of an XR, in particular near-infrared spectra matches with X-Loopy spectrum. And also the mass accretion rate is compatible with the one expected from an XR-like object. So yeah, thank you a lot for the attention.
Thank you very much, Eleonora. Okay, it's time for questions. There is no questions on chat. There is one question from Siegfried Van Averbeck. Siegfried, please.
Yes. Did you check whether the source is variable on a time scale up to a few hours?
Sorry, can you repeat, please? I haven't get it.
Yeah. Did you check whether the source is variable on a time scale up to a few hours?
Few hours. Actually, so we haven't done spectroscopic follow-up on few hours, but I mean here we can see that the variability is on a time scale of years. So of course there is a variability on the time scale of years. We've done some spectroscopy on months, but No, I don't think we have robust results in terms of days or hours.
That will be interesting to check.
Yes, thanks. It's a really nice comment.
Okay, thank you very much again. Very nice work. Let's move on. The next speaker is Sumedha. Sumedha Biswas from Radboud University. And the presentation will be about the Gaia and Merlich observations.
Yeah, okay. So hi everybody, I'm Sumedha Biswas. I'm a first year PhD candidate at Radboud University in the Netherlands. So during my PhD, we've been working on various ways to do electromagnetic follow-up of gravitational waves. And in the same way, we've been trying to work on a project where we can use Gaia to do the same. So many people have been working on this project, including Peter Jonker, who is my primary PhD supervisor, Susanna, who most of you know, and also Paul Verswijk, who is more on the Melik side of things. So we keep talking about multi-messenger astronomy and how it's the next big thing. And so similarly along those lines, the main goal is to use Gaia for the discovery of electromagnetic counterparts of gravitational waves. And to do this, the main thing that we do need is improved sensitivity of the Gaia photometric science alert stream. So to do that, the main method is to publish an extra, relatively less pure alert stream called Gaia X, which I'll describe in the next slide. But this was basically proposed by Susanna in her paper in 2020. So the Gaia X alert stream, so one of the main things to note is that it allows a single detection to trigger an alert. So yesterday in Simon Hodgkin's talk, we heard how normally for the normal Gaia alerts stream, you need 2 detections in either field of view detectors to actually alert, to trigger an alert. But in this case, you just need 1. Secondly, fainter candidates are also included. So normally you have the limiting magnitude is around 19, whereas in this case, you also want to include ones that are a little more fainter, so at 20.7 magnitudes. And of course, the main problem with this sort of thing is that because it's technically less pure, we would also have to eliminate the sources that we already know about. So, also you have limited sky coverage to consider. So in this plot, again from the same paper, you see, so all the gray regions are the regions that have been excluded from this analysis, and these are all the sources in Gaia data release 2. So the Milky Way bulge, the disk, the magellanic clouds, and totally about 21% of the sky was completely removed for this purpose. So this plot is one that all of you have seen many times. So we had other people in the group who actually sat down and manually checked the gravitational wave detections with the Gaia alerts that were published via GCN servers. And at least 50 candidates were found. So that is very promising. And obviously, if we actually do use the Gaia X alert stream, we might find some more. So the experiment itself was basically designed to test the Gaia X alert stream before actually turning it on during 04. So this was just the official announcement. You can find it at the link below. And this image was also included there, which was also from the same paper. So before I actually talk about the experiment itself, it's good to know what Melik really is. So Melik quite literally in Dutch translates to more light. And it's a very unique telescope because it both listens and looks at the sky at the same time. And what I mean by that is it basically gives us an optical view of the transient radio sky. So Melik gets triggered by Meerkat, which is South Africa's precursor to the square kilometer array. So once you actually have a transient radio trigger, that's when Melik actually goes in and observes optically. So in that sense, it gives us a very broad contemporaneous view of the southern skies. And Melik is based in Sutherland in South Africa with a 0.65 meter telescope and a wide field of view of 2.7 square degrees. Another interesting fact is that it's the prototype of Black Gem, which is based in Chile. So the teams working with Melik and Black Gem are very almost the same. And Black Gem has a slightly different science goal where we try, the idea is to optically follow up gravitational wave events. So the experiment itself, the idea of that was for MELIC to actually follow Gaia around, and in the process have a Gaia X alert stream published, so that we could actually check what kind of data we're getting and what kind of filtering techniques we need for the Gaia X alert stream. So what we're expecting in the process is potentially 3 scenarios. So the first scenario is when we have a match in both Gaia X and MELIC, both detectors have detected something, which could potentially mean that it's a true detection. That means we're actually seeing something. So of course you have the possibility of an interesting transient detection. But additionally, what it could help with is treating the machine learning algorithms that go into MELIC. So there's a big group within MELIC to actually work on this. So it could potentially help with that aspect as well. Secondly, maybe Gaia X detected something, but MELIC did not. So one of the obvious problems with this is that MELIC is on the ground and Gaia is in space. So with that, the problem is that, of course, MELIC is bound by the weather and the phases of the moon and things like that. So that could be an issue right off the bat. But if we know that both of them were observing and we still don't see a detection in MELIC, that could potentially help us basically better the Gaia X alerts filtering. And also we could actually go into the MELIC database and look at the environment using the MELIC images. And the third case is when we have a detection from MELIC, but not from Gaia X. So this could potentially help MELIC basically improve its bogus detections, because MELIC does pick up a fair share of detections of asteroids and things like that. So it could definitely help with that. So this is just like an overall simplified version of what we're expecting generally. So the current status of the experiment is it's still ongoing. So as you can tell, it just concluded. It went from September to October, almost I think the first week of November. So about maybe a week ago, it was finally done. So there's a lot to do still. But so I just added this plot to give you an idea of what we're actually dealing with. So this is a plot showing you the matches between Gaia X and MELIC, only from 1st to 15th September, because so I started analyzing just a little bit, so that once we have the analysis pipeline done, we can just deal with a lot more data. So this is an RA depth plot on the X and Y axes, both in degrees. And the blue dots in the background are the MELIC field centers. So those are basically, so for MELIC and also Traction, because they're very similar, the entire sky is divided into a grid with fixed sky locations. So that's basically what you see with the blue dots, with it's the centers of each of these boxes. And the red dots are the ones we have from MELIC, and the yellow ones are from Gaia. So this is a slightly zoomed in version just to give you a better idea, but we do see that there are certain overlapping points. So the next step would be to actually go into the MELIC database and look at the images and see what kind of environments and things we're actually dealing with. Additionally, this plot might also help you understand a bit better about the number of sources we're dealing with. So this is basically a time difference between MELIC and Gaia X matches plot, also between the same leads. And so on the y-axis, you have the number of sources, and on the x-axis, the number of minutes. So for example, around 8 minutes, you see that we easily have around maybe 300 sources. But of course, this is a huge number. And then eventually with more filtering, we'll finally probably only have a few possible candidates. And this is also just for 15 days. So it's definitely a work in progress at this point of time. So just to sort of summarize what I've talked about so far, so our main goal is to use Gaia to detect the optical counterparts of gravitational wave events during O4. And O4, the last time I checked, is scheduled to start in September 2022. So we have less than a year. So we decided to introduce a Gaia X alert stream to achieve this, but we also had to test it ahead of O4 to see if it's working okay. And we did this by basically running this contemporaneous experiment with MELIC. And effectively, what we've seen so far is that there's a lot of promising data and lots of analyzing left to do, which is primarily my job. And finally, just get ready for O4 because there's a lot to do. Thanks for listening.
Thank you very much, Sumedha. Perfect. Our timing. Okay, we have time for 2-3 questions. Okay, Łukasz is raising a hand.
I raised my Zoom hand as well. So this is a small telescope, mainly. But Jenna, I started with that this is an excellent idea to follow this. And I know that we were thinking about it for a long time, but eventually someone made it great. But then this is a small telescope, right? Half of what Gaia is, right? So there are different limiting magnitudes.
Yeah.
But is it kind of counted into account? So is there a longer exposure on the side of Merli? Are the depths similar?
So the thing is, because Mulek's been observing for a while, so you have multiple images of the same portion of the sky. So I think that could kind of help with that.
Yeah, but for the contemporaneous observations, you would like to reach the same depth. Right?
Yeah, that's true. So then you would have a bit of a difference. That would come under one of those cases where Gaia observes something and Mulek doesn't.
And there is,
yeah, there are.
You see it already. Faint ones are not seen in Merli because of the obvious.
Yeah, that is definitely a problem. But yeah. There are some limiting constraints where you have to work around.
And I guess most of the Gaia X things are very faint, right? They're like 20 or 19.
Yeah, a lot of them, yeah.
Well, that's cool. And thank you.
Okay, the next question, Vasilis.
Just following up to what Lucas said, but since you use Gaia as an alert, can you just go deeper? Because Gaia's exposure are not that long, right?
Very short. Yeah.
So in principle, you could go as deep or even deeper in, 4 or 16 times the observing time, because you have the alert, so you have a triangle. I was just wondering, right?
But I think they want to catch up with Gaia, so they don't have much time.
Because you want to follow Brackish waves, which doesn't give you a lot of time generally. So normally what they do is they have, with both the detectors, they verify, okay, we've seen it in both detectors. In this case, you're just dealing with one because you want it to be faster. Because I think roughly for gravitational wave events, up to a week after the merger, you can still, Gaia can still detect the optical follow. Yeah, longer than it goes away. So.
Okay.
So the Merli is following Gaia. They observe the same field of view at the same moment of time.
Yeah.
But how about the other field of view? Which field of view is Merli following? Because there are two fields of view in Gaia.
I have mixed the names up, but it is only following one. I know that.
Only following one, yes. And the detection can happen in any.
Yeah.
Yes.
As far as I know.
Okay, thank you, Sumedha. Let's move on. Now Hank Corbett from University of North Carolina will tell us about the transients monitoring with the Everyscope. Hank, are you there?
Hey. Yes, I'm here. Thanks.
Okay.
Share my screen.
Would you share? Yeah.
Okay, can you see my keynote and not the meeting agenda? Okay, and
yes.
You just see the, okay. Okay, so do you see the correct screen?
Yes, we hear you. Okay. We see your slides. You can start.
Perfect. All right. Hey, everyone. Good morning, according to my window here. So today I'd like to tell you about the capabilities and status of a couple of projects where our team is working on here at the University of North Carolina. Our current active survey over here on the left, the Everyscopes, and also the next-gen system we're currently building at the Argus Array. So both of these systems take a somewhat unusual, at least in the optical, approach to survey strategy. So instead of tiling out the sky, we're combining lots of small aperture telescopes to cover a large fraction of the sky simultaneously. So aperture is great, but quantity also works. These are the Everyscopes. We have one in the north in Southern California and one in the south on Cerro Tololo. Simultaneously, the two systems cover about 16,512 square degrees with 13 arcsecond resolution. So pixel size wise, somewhere between the NASA Kepler and TESS missions. The all-sky cadence is 2 minutes. So each full mosaic image, roughly 1.3 gigapixels in size, is every 2 minutes. At each site, we have 22 or 24 telescopes, 22 in the north, 24 in the south, each of which is just a 6 centimeter DSLR camera lens. And they're all inside of this fiberglass enclosure and paired to 30 megapixel cooled CCDs. So this is really a general purpose survey. We're capable of providing long-term light curves for everything brighter than about 15th and G-band, but also of doing transient detection in the Everyscope data directly. So this is a sky map of our depth as a function of sky position. This is specifically for Everyscope South, the CTIO system, but the numbers are very compatible with what we see in the north. As somebody mentioned yesterday, that Gaia is not afraid of the galactic plane. That's one of the great strengths of the survey, but we certainly have reason to be. We lose about a magnitude relative to this all sky average. You'll notice there's a secondary pattern here. That's the tiling pattern of the sensors. So lost my mouse. If you look in the lower left there, you can see the telescopes are arranged in bands of declination. So what you're seeing is just the sort of dead zones between those bands, or at least the areas where the image quality falls off and there's vignetting. Photometric uncertainties range from about 1.5% at the bright end to 10% at G-band 15, which I can talk more about in a second. Over the course of a night, we'll cover about 30,000 square degrees over those 40-some cameras. Each one of those cameras covers almost 400 square degrees on its own, with an average of about 200,000 stars. We can zoom in a little more, and you can get a sense of the density in the time domain. So we're really getting hundreds of epochs over the whole sky every night. And the first thing this lets us do is we build up a really large database of photometry over time. So every night we're collecting those hundreds of measurements for something like 8 million stars, 20 million in total within our depth range. And over the past 7 years, this has added up to about 2 trillion photometric data points, plus an additional roughly petabyte of imaging data. So due to that large number of photometric measurements, we can approach few millimag photometric performance with binning, as you can see in this nice compact binary light curve. But because of the sheer amount of data, we have the flexibility to detect these really short duration events in light curves. Like this is a young star with a rotation period, where we can see these nice flares popping out. And each one of these flares is less than an hour long, but they're nicely sampled in the 2-minute cadence Everyscope light curve. So in addition to the light curves, we've also built a low latency detection pipeline for direct detection in our images that we call the Everyscope Fast Transient Engine. So this can monitor the whole 16,000 square degree field of view for variable sources in real time. And these candidates are typically inserted into our databases here in Chapel Hill for each image before the next 2-minute image is actually written to disk. So that includes some automated vetting, cross-matching with a variety of external reference catalogs and also internal catalogs, so deduplication with previous events and association with previous detections. And this whole pipeline is built around a relatively straightforward direct subtraction algorithm. So each image is normalized to its noise and then subtracted from a previous image in the pointing. The whole Everyscope dome will track the sky for about 2 hours before having to ratchet back to a start position. So basically we hit the horizon after 2 hours. So we take 2 images from each one of those ratchets, typically with a 10-minute lag between images. So this simplifies a lot of the PSF matching issues that are common in image subtraction pipelines. But it also means that our sensitivity peaks sharply for really rapidly evolving events. So things that behave a lot like indoor flares, which you can see on the right here. This also demonstrates how that rolling reference frame works, where you can see in the first film strip of reference science and difference image, that science image becomes the reference image at the very bottom at 9:06 UT. At the moment, we don't have a public event stream, but we certainly like to have a couple of different things we're considering for making that happen relatively soon, within a year at least. So very interested in the discussion happening earlier about the degree of contamination that's permissible in a public event stream. So I'd like to highlight really quickly one of the projects that really motivates the low latency event stream that we have for Everyscope, which is using FD for rapid spectroscopic follow-up of M-dwarf superflares. So these are flares that are common across the sky. We see 3 or 4 per night, but they're individually short-lived and they're rare for any particular star. So it's difficult to get a really heterogeneous spectroscopic sample, especially for the really high energy events. And these flares, they're responsible for a lot of the UV environments on rocky planets around cool stars. So they inform habitability models. So there's a balance between having enough UV flux to power prebiotic chemistry while also not having too much to destroy an atmosphere. So understanding these UV environments that's created by flares, or at least mediated by flares, really depends on the earliest phases of these events and what's happening, and with relative backbody to line emission and characteristic timescales. This is information that's really only known for a handful of stars that are extremely active. So this program, currently ongoing, is trying to increase that number of early time flare spectra using the Goodman spectrograph on the SOAR 4 meter over here on the right. We've probably had 5 or 6 nights in the past year and roughly as many flares. So this plot shows one from earlier this year. It's a movie, hopefully it'll play. So you can see a hot black body spectrum that is sort of fades out to line emission and gives after the first 20 minutes or so. This is the fastest we've managed to get on one with SOAR yet. This is 6 minutes after the 6 minutes 30 seconds after the peak. So this is kind of a mixed queue and observing mode where we're sitting at the telescope waiting for something to happen. Okay, so for the last 3 minutes of my talk, I'd like to tell you about the new instrument we're currently developing. The past few years, there's been this really huge sea change in the availability of relatively cheap, off-the-shelf, wide-field astrographs, really aimed at astrophotographers and at amateurs. So what this really has done is it's made it feasible to scale up an every scope-like design to much larger apertures. So this is a reference design for what we're calling the Argus optical array. The design is very similar to every scope, but with a few key differences. The biggest thing is sizing up to fit the number of telescopes we need for the field of view. So 900-ish telescopes, and also adding things like thermal control. So rather than having a bunch of telescopes that are exposed to the elements like we have with every scope, we want to keep everything thermally controlled so the focus is stable, simplifies cleaning a lot. So rather than having to go through a complicated cleaning procedure with the optics, we can basically hose the thing off every few months. Basically just scaling issues going up to this many telescopes. Okay. This is a brief overview of the specifications for what a complete 900 telescope system would look like with an equivalent field of view to the every scope. But we're stepping down to what we get from these now 200 millimeter aperture telescopes is 1.4 arcsecond pixels, roughly 1% the area of an every scope pixel. So that gives us an additional 4 magnitudes of depth versus every scope, 1 minute cadence. And also because we're moving to CMOS detectors that are related tangentially to basically cell phone sensors, they have extremely low readout noise and much faster readout speeds than conventional CCDs. So we're working on a 1 second cadence mode that would get us the whole sky every second down to roughly the same depth as every scope. Our current state, we're working through a stage test program with the NSF, culminating in the construction of this system, which is funded jointly by the NSF and at the Schmidt Futures Foundation. This would get us the entire northern sky every night, and with roughly 38 telescopes, plus or minus a few, and providing about 10 minutes of coverage per night at high cadence. This is currently fully funded, and we're hoping to have this on Sky sometime mid-2022. We have a earlier prototype with 9 cameras that will be on Sky, hopefully by the end of next month. It's constructed here in Chapel Hill, it just needs to be transported. And finally, I'll leave you with this brief list of applications that folks on our science team are interested in working on with the Argus array. We're always interested in building a science team. So if you have something you think would benefit from our data, like follow-up and confirmation of Gaia transients, I'd love to talk to you about it.
Okay, thank you very much, Hong. It's quite impressive. Is there any question? Yes, Łukasz, please.
Hi, Hank, Łukasz Wyrzykowski. This is very impressive indeed. And I'm actually very much interested in the archive you've built up there.
Sure.
You've been observing the southern hemisphere since 2015, more or less the time we started the Gaia alerts. So you have light curves for everything what we found with high cadence. Can we get that?
Yeah. Absolutely. Sure. I think there's a depth offset that's significant, but we certainly should have some data that you could bin up to find things. And we would, of course, be glad to share whatever.
Excellent.
I'll get at the moment. That'd be great. We have a public light curves interface in the works. I'm not sure if it's actually been deployed yet, but if you need things that aren't in our archive, we can make one-off light curves very quickly and easily. We're equipped for that. So,
Okay,
glad to work.
great, excellent. Yeah, and another very quick question. So since you use SOAR telescope, so there was a talk yesterday by Rachel Street about AON system and TOM system. So SOAR is part of this. So you can possibly, I don't know if you've been thinking about this, but you can connect to SOAR via EON system, so that then you can do the things like you show here in the follow-up in an automated way. Probably something you thought about that. Just to...
Yeah, we're very interested in that. We're currently using some of the back-end software that was developed for AON, but using it directly sitting at the telescope. So if there's a way for us to get integrated into TOM more fully, I think that'd be great for us.
Okay, cool. Thank you.
Okay, thank you very much again. So now there is time for the new robotic telescope observing model, which will be presented by Helen Jermak from Liverpool John Moores University. Helen, you can share your screen.
Right, can you hear me and see that?
We can hear you very well. We see your presentation, and now there is in full screen mode, so you can start. Thanks.
Okay, great. Well, thank you very much for inviting me to come and speak about the new robotic telescope. I certainly hope that there's some new and exciting updates that I can share with you, because I feel like I've been given this talk quite a few times, and every time there's no money, but yeah, there's some more positive news now. So yeah, I'm Helen Jermak. I'm the project scientist for the new robotic telescope, and today I'm really going to focus on talking about our observing model. So I'm going to do a very brief introduction to the project, but if you want more information, please do drop me a message on Slack. So the new robotic telescope, the NRT, is going to be a 4-meter class robotic telescope, and it's actually going to have 18 individual hexagonal segments in its mirror. And this might, horrify some people that it's not going to be a monolithic mirror, but actually this works really well for a robotic autonomous facility, because we can do regular maintenance of these smaller segments without disrupting the observation. And it also means that we have quite a lightweight telescope. We remove a lot of the weight, so we can move quite quickly. So the telescope is designed for a rapid follow-up of transient sources, and we're actually aiming to go from our 2 minutes from alert to source that we have with the Liverpool telescope at the moment, and make that just 30 seconds. So really, really rapid response and rapid slew across the sky. So currently we have first light planned for 2025. This is likely to be engineering first light, with proper science first light maybe pushed to 2026. So as I said, our objectives and goals are to be the first ground-based facility on target. We're going to, again, follow the Liverpool telescope model where we're fully robotic and autonomous. So very low maintenance, very few staff on the island. And actually during COVID, we showed that it's possible for a facility to continue observing without anyone visiting for months on end. And so the area of astrophysics we're focusing on is the time domain. So the image at the bottom of the screen just shows the future site for the telescope, which will be the Carlsberg Meridian Telescope site. We've actually had approval of this now, so that will be where we build. It looks very close to WHT, but the WHT doesn't impact our field of view. There's a possibility that future observatories on the island may impact this field of view very slightly, but we've done an analysis of this, and it's no disruption to the science case. So our funding status is quite positive now. We've received funding from the UK Research Council, STFC. We received that this year, and that's really great. That's funded all the UK work packages. So we're moving forward with our preliminary design review at the moment. So we have Spanish partners who have secured their funding, and there is outstanding funding still. So if anyone wants to get involved, especially with particular work packages based on the kind of infrastructure in your country, then please do get in touch. But we are moving ahead with the project. We are starting to do all kinds of stuff at site. with the intention of groundbreaking very soon. So this is just a histogram showing the science areas for the Liverpool telescope. And NRT is very much going to be a bigger, better version of the LT, following a lot of the same kind of science. But one of the reasons I'm giving this talk is that the science areas might be very similar. The telescope might be kind of just like an optimized version, but actually our observing model will very possibly be slightly different. And this is what I want people's feedback on. So this figure just shows the different proposals or applications to the Liverpool telescope based on the science area. So obviously you can see these span all kinds of different aspects of time domain astronomy. And so where you see active galaxies there, that's the kind of variable objects like blazars. And so this forms our the areas for our science working groups for the NRT, and these are open, and if people want to join to contribute, you're very welcome to do so. So we have supernovae, gamma ray bursts, tidal disruption events and AGN, stellar astrophysics, exoplanets and solar system bodies, and electromagnetic counterparts. So more information on these can be found on the NRT website, but that's not really the focus of this talk. You know, these are I would imagine that everyone here covers at least one aspect of these science areas. There is also the science goal of doing follow-up to survey. So not exclusively the Vera Rubin Observatory LSST survey, but you know, any kind of transient surveys, either ground-based or space-based, we plan to do some kind of alert follow-up. But this figure just shows that even though we're in the Northern Hemisphere, there is significant sky overlap with the Southern Hemisphere. And so we do anticipate a lot of LSST alerts to be followed up. So to move on to the observing strategy, some of you may be aware of the way that LT works. You know, I've already seen presentations where people have used LT data. But so typically, you know, with target of opportunity science, the way that the telescope works at the moment is that people have assigned data, assigned observing time, and they use that time to follow up objects. But it's not really possible for specific objects to be assigned to specific users, and this can lead to duplication. So if there's an alert released, you know, people from supernova science might follow it up. You know, people from Nova Science or all different kinds of science groups will request observations of the same source, and this can involve duplication, and then some groups just won't use the data at all. So a PI might waste some of their time allocation on following up objects that might not actually be of much interest to them once they've classified what the object is. Because one of the big drivers on the NRT is spectroscopic classification. And so in a recent paper, Senko et al. Said that target of opportunity policies are constructed to encourage groups to pool resources and work together where sensible and maximize the science possible from any given data set. And so this is really kind of the model that we're trying to adopt with our observing strategy. Is it's much better to pool resources to make the observing more efficient than it is to just have exclusive access to certain objects. So the scheduler will be kind of split into two components. So typically we'll have the traditional robotic scheduler. For those of you who use the LT, this is, you know, you apply for time based on your science case, and you're allotted a certain priority and amount of time. And you use this to, you know, you upload your own targets, you upload the things you want to do, and the automatic scheduler will decide which objects are best to observe based on a variety of different conditions, including weather, science priority, and then some kind of random allocation as well. So it's not always the same source. And so this kind of operation mode will continue on NRT, and all the instrumentation will be available to these users. And this will be approximately 60%. This is a kind of an estimate at the moment of observing time split between the different funding partners. And this kind of observation will consist of all these different kinds. So ultra rapid, you know, so that's the kind of stuff that might fade within a minute or minute scale. Rapid, so things that are, you know, urgent but not within that ultra rapid time frame. Got timely stuff that you want to follow up within the next 24 hours. And then you've got kind of quasi-simultaneous observation. So that might be fixed groups or kind of long-term monitoring. So this is kind of what the LT does. This is, very similar model. But what I want to talk about in like the last couple of minutes of my time is this spec survey that we're proposing to do. So this will be approximately 40% of the NRT observing time. And this is mainly spectroscopic, but there might be some aspects of polarimetric follow-up of survey targets, especially the rapidly fading ones. And so this will be kind of general access data where the telescope will do a variety of follow-up of these kind of objects and these kind of alerts. And then the data will be available through all telescope users. So people can access these, look at the classification and decide whether they want to use their own allocated time to do further follow-up, maybe with longer exposures, different instrumentation, that kind of thing. And hopefully this will avoid multiple observations of the same object being scheduled, which can happen at the moment. It's fairly rare, but it can happen. So the way that this will work is we obviously need people to select these objects. So we'll have a panel of kind of individuals who will assign the targets and prioritize targets. And this is an ongoing area that we're working on. And we have a PhD project where David Law is working with the NRT team and the computer science department at Liverpool John Moores to look at LT data, to look at simulated data, try and understand what we'll start getting through from LSST and other surveys to make sure that when we're hitting the sky in 2025, 2026, we know what to expect. So I'll summarize there. We've got CCI approval on La Palma, the NRT's got its green light to go ahead. And our preliminary design review is happening at the end of this month. So we're really making progress. And we really welcome all kinds of different partners to get involved with the project, be that, for specific work packages or instrumentation, with the kind of in-kind contributions, but also really the spec survey. I really want people to get involved and to tell me what they think of it. And any learned experiences or any kind of input like that would be great. So obviously I'm on Slack, so you can drop me a message on Slack, or my email address is here, or there's also the website where you can have a bit more of a look and you can also get in touch through there. So that's where I'll end. And I just have an additional slide just because not all of the components of this talk are my own work. So that's just there. Thank you.
Thank you very much, Helen. It's time for questions. There are no questions. There is question from Ruta.
Yeah.
Ruta, you can ask your question.
Yes. Yeah. How many people does it really need to be at the observatory? None, 1, 2. There are really a number of people. Yeah.
Sorry, I had a little bit of trouble hearing that question. Do you say how many people need to be at the observatory?
Yes, how many people? What was least as you had to be and most, I think, yeah.
I mean, the question is about the observers, right?
Yes,
what is the number of observers?
Yes, because it looks like it's fully automated, but you told that there was people. So what is the number? And why, of course?
Okay, so do you mean the people who assign the targets for the spec survey? Is that?
No, I wanted to ask on the
people.
Yes, on the site. Yes, thank you. On the site, yeah.
On site.
People on. Yeah.
Technicians, engineers.
Yeah, technicians, engineers. Yeah.
Okay, yeah. So for the Liverpool telescope, we have one part-time engineer who is based in La Palma, and he goes up maybe 2 times a week to do kind of general maintenance and general health and safety checks. Otherwise, there's no one else on site, and we haven't had anyone on site since before COVID. So I think it was January January 2020 that we had someone other than our general engineering staff on site. And so we essentially have operated through that time without anyone from the UK visiting. We're closed at the moment due to the volcano, but that's obviously, beyond our control. But typically we don't have anyone there. But, during the nighttime observations, no one's there. We have a duty officer based in the UK or the US who will check things at the start of the night. So we'll make sure that there's no heavy dust levels or anything like that. We'll put the telescope into operational mode, and then the telescope does its own thing all night.
Okay, Marco Lam.
Hello, can you hear me?
Yeah.
Yes, sure.
Excellent. Hi. Yeah, many congratulations. I've been sitting next to you for 3 years, and finally got some money. So I'm just wondering, how would the time be distributed among the different funders? And for example, in the spec survey, who can join it? And finally, say if Opticon Radio Net want to get some time off the telescope, how much would be possible?
So similar to LT, Opticon will have access to the telescope. That kind of stuff hasn't been ironed out and agreed just yet, but we certainly want this data to be available as widely as possible. There hasn't actually been a full agreement about percentages per partner and how in-kind contributions compare to direct financial contributions and things like that. So it's all to be worked out. And that will kind of be reflected in the panel of people assigning these targets for the spec survey. But we are still very much in a process of understanding the different contributions and how that will relate to output. But I'm very sure there'll be Opticon Radio Net components to the NRT, similar to the way the LT works.
Thank you.
Okay, and the last question from David Buckley.
Yeah, hi Helen. It's nice to see the developments happening with NRT. It's really great. You may have mentioned it, but what's the revised cost for the telescope? Telescope only.
Oh, I'm not sure, off the top of my head, I'm not sure. The total project is about 28 million now.
Pounds?
Pounds, yeah, sorry. Euros, sorry.
Euros, okay.
So you'd have to drop me a message and I'll speak to the engineers, and I'll we've recently done it like a breakdown of costs, so I can let you know that. Just off the top of my head, I couldn't tell you.
Right, thanks.
Okay, let's move on. Thanks, Helen, again. The last talk before the coffee break will be about Skilakas Observatory and the Transient Universe made by Vasilis Harmandaris, the director of 4th and Skilakas Observatory. Vasilis, please.
Thank you very much, everybody. I'll try to give you a brief presentation about Skilakas and what we've been doing lately, in particular for those who are not here and won't be able to visit the facility with us tomorrow morning. So Skilakas is a joint research infrastructure of the University of Crete and 4th, and it's managed by the Institute of Astrophysics, where I happen to be the director. So the institute, which operates Skilakas, is actually a boutique institute, as we used to say, and it's focused on excellence. And since we are in Greece, I had to put some Greek, ancient Greek without accent. And there is a saying by Thucydides, which in Greek says, "Andes garpoli ke utihi," which effectively means that it is the men and women who make a city, not its walls, stressing the importance of personnel in making discoveries, as we all know. So currently the institute consists of 8 researchers, 8 tenure researchers, a few technicians. We have 9 postdocs, 13 PhD students, and 4 master students. It was created 3 years ago, and the reason why it was created was because there was already a team existing here doing astronomy over the past few years, which was fairly successful, and the government recognized that. I give you some numbers here, but the important thing to sort of like remember, if you use ERCs and as metric of excellence, we have 2 of the 3 ERCs awarded in whole Greece are here at the Institute, and 5 other scientists of us passed from phase B, but they were not funded. We have the most-cited researchers in Greece, as well as we trained a number of students and postdocs. A sufficient fraction of those actually got permanent positions outside Greece. We are happy to say that Aga, who was with us many years ago, actually is the chair of ORP board now, and she's very successful back in Poland. Recently, a couple of the PhD students that we were trained got the Best Thesis Award by the International Astronomical Union, and then Gina Panopoulou got Hubble Fellowship, as well as the Merak Prize by Aris Tritzis of the European Astronomical Society, who has since obtained an Additional Fellowship in Switzerland, which we all know that it's fairly competitive as well. Scientifically, the facility has produced nearly 250 papers and 15 PhD theses from Greece and outside Greece, and a couple of these papers were Nature papers, and Aga was involved in one of them, actually, with the Optima instrument. So our success, I think, is partly due to the international profile we have, and also thanks to the fact that we are in Crete. We can attract, because of the weather and the sea, excellent scientists from all over the world who want to come and collaborate with us, either in long-term or short-term visits. And since we recruit heavily from people who are abroad, we have been able to maintain very strong collaborations with the key leading institutions, and I cite a few of those in France, Germany, US, and in the UK. So the observatory that we will visit tomorrow morning, you can see a picture here. It started with a 0.3 meter telescope back in 1995. The guest house was built right afterwards. The 1.3 meter telescope was built in 1995. And at the time, actually, we installed a photovoltaic so that it has power this way. And there is a new dome, which you will see later on, which is being constructed, where we hope to be able to house a new 1.2 meter robotic telescope. And if someone gives us some extra funding, we will name the telescope after that. So the observatory is located at an altitude of 1,750 meters. There's excellent seeing conditions due to laminar airflow. You can actually see this nice image of the Aegean Sea. You can see the weather comes from the north, and you have steady flow as we reach the island from the north, and Skinakas is very close to the north side of the island, so we actually have limited turbulence. The current infrastructure investment is in the order of 4 million euros. One of that was contributed by MPE, who was a partner for the first 30 years of operations. And we expect that this infrastructure investment will double in the next 3 years, so that will make it easier. So, as I mentioned, we had a 0.3 meter wide field telescope, and then the 1.3 meter was installed later on. And we were able, thanks to the efforts of the previous generation of scientists, to have it very well equipped. With optical cameras, near-infrared camera, we had the Optima camera from MPE, which was a fast photometer, Robopol, which operates now, and we have Wallop that I'll mention to you later on. It's funded by an ERC project. Here you can see the 0.3 meter telescope, the 1.3 meter telescope, and the upgrades that are taking place right now. We are building a new building. You will see it later on. We got a new 5 meter dome. That was from an Interreg program between Cyprus and Greece. And that building, we hope that it will house eventually a 1.2 meter robotic telescope. We have secured some funding. We expect additional. And that telescope will also add an applied research component to the work that we've been doing so far, which was originally education of the students of the University of Crete and research. And it will be used for satellite monitoring. We have there is a European Commission project for that, and we have been vetted to do that. And it will be used as a test bed for ESA's latest telecom projects. You may know of Skylight. We have been selected as a site for that, and we hope that to be able to develop close synergies with other institutes and groups at FORT who are experts in quantum optics and telecom activities. And that will be beneficial for me as a director because I need to care about expenses and it will cover actually some of the operational costs. This is a new building. You will see tomorrow. It actually exists as of last week. The dome was placed almost a month ago. We expect that all construction will finish at the end of this year. Currently, what we will do is that we will put in this dome the old 0.6 meter telescope we had, which is the robotic telescope. Upgrades in software guiding was done in Germany. We'll put it when we reopen in March. This is very convenient because it can do rapid follow-up of transients. You can monitor astrophysical objects easily. The amateurs of the Tübingen area are using it for astrophotography, and it will also do some of the supplied research I mentioned earlier on. We're also very lucky because the region of Crete actually recognizes our efforts, so they secure funding to repair the road. The last 5 kilometers that are off the main road, you will see tomorrow, will be paved once more. It's paved road, but it wasn't repaired extensively for the past 20 years. And the contract has been awarded. Construction will start in next year. And also we secured another $1 million to create a visitor center, which will be very helpful for us because we often have open nights and it's a very popular attraction for a number of public activities. And we are also in the process of actually connecting Skinnakas to the electric grid, which is essential if we want to be more operational, more for applied research that I mentioned. If you were to go to time domain, there was work that was done in the past by colleagues here following quasar monitoring for many years. But more recently, since 2013, we installed the Robocall instrument, which is a free-filtered polarimeter, which with no moving parts and very, very low systematics. It has already produced 13 refereed papers, and it was a collaboration between us, Calvete, Max Planck in Bonn, and India and Poland as well. It was used originally for blazar monitoring, Fermi blazars, but in the process it was used essentially to also observe GRBs, BE X-ray binaries, because some people here are working on that. And it actually contributed substantially through the measurements that it obtained to propose and secure the Pacify ERC projects and the Wallo polarimeters that I will show you in the next slide. And this is actually this project, the PI of this project is Costastasis, and the goal is to measure the magnetic field of our galaxy, doing very interesting work combining with Gaia data. Basically, the idea is to measure stellar optical polarization using very sensitive polarimeters that are bound to be constructed. They have less than 41% accuracy in the systematics. So since most of the polarization comes from the magnetic field in molecular clouds, and with this magnetic field, basically what it does, it aligns the grains along the directions of the magnetic field. What one can do is that you can combine the measurements of the polarizations of the stars with the stellar distances, which are measured by Gaia, and effectively measure the magnetic field in between stars by solving the inverse problem, and thus creating the 3D structure of the galactic magnetic field. The added advantage, which has never been this directly deliverable of the project, and that will, in addition to that, which is already very novel, it will aid in removing the polarization background from the CMB maps, polarization maps, and thus putting very stringent limits to the B modes that are being solved by the community who does cosmology. Obviously, this project, even though it does a survey mode, it will do targets of opportunity. It consists of 2 telescopes. The 1.3 meter telescopes here in Skinnakas and a 1 meter telescope in Sutherland, South Africa, that we showed earlier on. And here you can see the design of the two polarimeters. We expect that these polarimeters will be on the telescopes in spring for the southern side and late summer. Here at Skinnacas, we're expecting to start earlier, but due to COVID, most of the factories had problems. However, it was actually very nice because if you see that the importance of the science that will be done was stressed by the decadal survey in astronomy that was released a few days ago. And it's interesting to actually see that the decadal survey mentions explicitly the difficulty in establishing the 3D magnetic field and how important it is that big data produced by Gaia can be used to create a 3D view of the ISL using magnetic field measurements. And it measures, as you can see, Pacify explicitly as a key project that may produce spectacular results in addition to the results that have been done now. So we are very optimistic that this project will provide interesting results. And the real-time domain work that will be done at Skinnacas is actually will be done by the Turbo telescope. Turbo is the total coverage ultra-fast response to binary emergence observatory. This was a proposal by Pat Kelly at the University of Minnesota in the US, and will actually be giving a talk on that in detail on Friday. And the idea is to have 16 11-inch telescopes that will have 240 degrees square degrees field of view, 16 in Crete and 16 in New Mexico in the US. And you can actually, they are in a very fast plane wave mount. You can actually see the original design to the right where the telescope can point within 2 seconds at any part of the sky. This was the original design with 8-inch telescopes. Now Pat is able to actually produce, actually do the same thing with the 11-inch telescopes. Here you can actually see the new telescopes next to a typically graduate student at the University of Minnesota. And this will be placed actually on Skinnacas. You can actually see the site that we have selected. And we expect that this will be operational in 2023. And Pat will actually give more details about sensitivity and the cadence and how this can work very nicely with other surveys like ZDF, for example, combined, etc. Mostly for GW follow-ups, but doing also its own surveys. Pat will talk about this in detail. The weather in Skinnacas as well as in Crete is fairly good. You can actually see some statistics here. I'm not going to bother you. And I will just finish with the motto of our institute, which is the sky is not our limit. And here you can see a nice picture of the 1.3 meter telescope and the galaxy above Crete. Thank you very much.
Thank you for your talk, and thank you also for your hospitality. It's a great place. I can imagine that it's hard to work here because of the weather.
Yeah. It's, we need to have very disciplined people, not to be tempted.
Bring them from the northern country.
Yeah, this is, if they are not disciplined, just fine. But we've been doing well.
Okay. Any questions? I don't see questions, but I have one short question about the observing period. Do you observe during the whole night or have a break?
Whole year.
For whole year, yeah.
No, we don't observe the whole year. The reason why we didn't do it is we typically observe up until mid-December, and then we start again sometime in late March. The reason why we did that is because it costs to actually clean the road. It doesn't snow much. But since we didn't have access to resources, and we were using the telescope just for us, there was no need to do it. Since now we are moving into more operational mode and the applied research that I mentioned, it's not too expensive to actually clean it if you just clean the road every time it snows. It doesn't snow very frequently in Crete, as you can imagine. But if you don't clean the road, the snow will pile up at some places. So I think down the road, maybe in 2 years from now, we'll be able to operate throughout the year, even though the weather is not as good in the winter. It's still, I think, acceptable. Sort of like typical to what you would expect in Canary Islands without dust.
Okay, I see. Okay, thank you. Big thanks to all of the speakers and to you for participation in this session. Now we have, there is a time for a coffee break, but please note that there is a change in the schedule and this coffee break is really short. So we will meet back at 15:45 strict. Thank you. Okay. Welcome everybody after the coffee break. The first talk will be presented by Krzysztof Katarzyński, and will be about the searching for exoplanets by direct radio imaging. Krzysztof, please.
Okay, thank you very much. Thank you. Good morning, everyone. My name is Krzysztof Katarzyński. I'm astronomy at Nicolaus University in Poland. And this will be, I think, the second almost purely radio astronomical talk during this conference. And thanks to the yesterday excellent talk by Haro about the radio interference, I think I can skip many explanations during this talk, and this is very good because it was a very short time to present this. So I'm going to speak about the search for exoplanets by direct radio imaging that is somehow connected with the very precise astronometry and sorry, something for me. Okay, next page. So, what is the problem with detection of the exoplanets at radio frequencies? And as we know from, for example, from the solar system, Jupiter is emitting radio emission up to more or less 40 megahertz, which is problematic for most of the radio, very large baseline radio interferometers like EVN or VLBA, American interferometers. It can be basically observed by VLA or GMRT instruments, but those instruments have relatively small angular resolution and also quite small sensitivity. So we'd like to observe such objects and in principle try to detect by direct imaging some exoplanets using EVN, European VLB network, or very large baseline array in US. So basically we need objects, planets that will radiate in a gigahertz range, because in this range most of the interferometers, this large and global, I would say, interferometers works. So the main motivation for this work was to estimate possible gigahertz radio emission of extrasolar planets, and also I will speak also about the brown dwarfs, but these are also very interesting candidates for such investigation, for such search. So this is a comparison between the European VLBI network and the, for example, GMRT. I have not had too much time to go into details, but what is important in this picture that the sensitivity of the European VLBI network can be even 3 orders of magnitude better in comparison with this relatively small baseline interferometer. I mean, the size of this interferometer is just several kilometers. So there is also limitation in the angular resolution, but what is important also is the limitation in the sensitivity. And here you have the comparison between the different interferometric systems like LOFAR, GMRT, VLA, and EVN, and also American VLBA. And you have the comparison with the hypothetical planets with different orbital radiuses from 0.05 up to 5.2 astronomical units. 5.2 is of course more or less the Jupiter orbital radius. So you have the curve. There is a distance on the horizontal axis, and there is the separation in milliarc seconds. And what we can see, and the best I think what we can see, is the observation of the planet that is away about 0.05 astronomical units from the star, and this star is located at a distance about the 35 parsecs. So I think this is more or less the best what we can achieve with current global interferometers. But be careful, this can be done at 5 gigahertz. So the question is if we can observe such sources at 5 gigahertz. Yes, and the fundamental question is, shall we expect any radio emission from exoplanets at gigahertz frequencies? And the main parameter for such emission is the magnetic field. I have no time to discuss more, to explain more about the emission mechanism, but the frequency of the emission depends directly on the magnetic field strength, and because this is basically cyclotron frequency. So we need a magnetic field which is of the order of kilogausses to expect radio emission from about the 1.5 or 5 gigahertz. And for example, the Jupiter magnetic field is around a few gigahertz, here 14, 5 and 11 gigahertz, different positions in Jupiter. So this allows for the emission maximum about 40 megahertz. And we need planets that will generate magnetic field of the order of kilogauss or even more to be visible to radiate in radio wavelengths at the gigahertz frequencies. And the problem is that we don't know how the magnetic field in the planets is generated. We expect there is some dynamo process where the currents inducted by the liquid fluid in the interior of planets are generating this field. And well, we have several models. I have chosen one model which was published in Nature and in other papers some time ago, which directly connects the parameters of planets like mass, luminosity, and the radius with the expected magnetic field from such a process like a dynamo. And there's also the dipole magnetic field that is necessary for our calculations. So basically, it's just a scaling factor with the mass of the planet. And these are the parameters we are getting from the models. And what is also important is the age of the planet. Younger planets can generate stronger magnetic field, and this is the key parameter for our investigations. So here you have the age of a planet and the radius, and I mean the continuous lines describe more or less the planets. Maybe I should say from the beginning we are speaking about the planets like a Jupiter, so giant planets, and with the masses. I mean the planets are with the masses up to 14, 15 Jupiter masses. Above this limit, we can speak about the brown dwarfs. So the continuous lines shows the planets, and the dashed lines shows on these pictures already brown dwarfs. And here we have also luminosity with the age. This luminosity, of course, decreases with the age of the planets. And taking these modeled parameters of the planets, we can estimate the required magnetic field. And indeed, there is a chance to get some radio emission at the gigahertz frequencies here, and but only in the young planets with the age well below 1 billion years. So we have to look for planets, for the objects which are relatively young, and then looking for such stars with such planets, we decide to check the special kind of the stars. But before, I have to say also one word about the emission mechanism. And the emission mechanism is simply we assume similar mechanism like in the Jupiter case, where the magnetic field of the planet is interacting with the stellar wind of the star, and the kinetic energy of the star is dissipated in the magnetosphere of the planet, and this dissipation of the energy generates also the radio emission. So the general result from my calculation is that on this picture more or less. So here we have the frequency from 1 to 5.5 gigahertz, and we have the different aged objects with different ages from 0.05 gigayears up to 5 gigayears, and also the objects with different masses are connected with the dashed lines, and this U-like shape indicates the region where we can try to detect such emission with the global interferometers. So between 1.4 and 5 gigahertz more or less. And this, I must say that this is for 25 parsecs distance, because of course with the lower distance we can expect better detection threshold. And also this is for 5 hours of integration by the EVN network. Of course, increasing the integration time, we can lower this detection threshold, which is given by this horizontal line. So our calculation demonstrates that the strongest emission could be generated in the young systems as old as about a few hundred megayears. Therefore, we selected A-type stars in the solar neighborhood to check if we can expect any radio emission from such sources. Any emission from planets around such stars. It's relatively difficult to find planets around 9 sequence A-type star. With classical methods, there are, at the time when I was looking for this, there was just only 11 such stars. Maybe now this number is higher, but I think not much. And looking for star candidates that may host a young planets or brown dwarfs, we selected main sequence stars with the location located in near neighborhood, in the near solar neighborhood, a distance less than 30 parsecs. And this is the table with our stars. I will not go into details. All the stars are, of course, well known here, with the distances, masses, luminosities, radiuses, metallicities, ages. As you see, the age of most of the stars is less than 1 gigayear. And this is the result, expected radio emission at gigahertz frequencies from the planets located around such stars, with the mass about 15 Jupiter masses and located at the distance of 1 astronomical unit around selected A-type stars. So unfortunately, most of this emission, the estimated magnetic field is too low to generate emission at frequency higher than more or less 1 gigahertz. Most of the planets which could exist around these stars are located, should generate emission up to 1 gigahertz. Only in a few cases there is expected emission above 1 gigahertz at 2 or 3 gigahertz. So of course those planets are well known. Those stars are well known, and some of the planets around these stars are already discovered. So. But looking at this diagram, we see that the strongest radio emission should be expected around the Vega and Fomalhaut, which are here. But unfortunately, those stars are relatively old. The emission is strong because the distance is just small. But the stars are relatively old, and we expect that the planets there should be also old, and we should not expect emission at the frequency higher than 0.9 gigahertz there. In fact, there were observations and try for detection for such emission from planets, and there's only another limit of 4.8 gigahertz established. Direct imaging of the Fomalhaut lead to detection, of course, not at the radio wavelengths, detection of the planet located around the Fomalhaut. But this planet is at a distance of about 100 astronomical units, and this is too far. That the kinetic energy of the stellar wind is already too small to dissipate enough energy to be detected by current instruments. Vega is surrounded by debris disks that may suggest that they could be some planets, and this needs to be investigated. The other systems may be, since I have not too much time, 1 minute, so I will skip the description of this one of those systems. The best candidate is the nebula, which is quite young, just 45 million years, and located at a relatively small distance, 11 parsecs. Therefore, massive object there in the system should produce emission enough strong to be detected by current VLBI instruments. And so there was in fact such observation at 0.45 gigahertz of this star, but as you see from my prediction, this beta alone is should not radiate at such high frequency. The maximum of the emission should be expected 3 gigahertz. So maybe because of this, there is no such emission. So there is some possibility to find a planet by direct imaging at radio frequencies, but this is limited to very, very massive objects and the objects that are located close by in our solar neighborhood at the distances no more than, I think, 50 parsecs. So thank you for your attention.
Thank you very much. We have a question from Siegfried. I will read it. Are you sensitive to aurora emission from the host stars in analogy with the Jupiter Io system?
Yes, I did the calculation, and in the paper that I published, there are estimation of such emission of this emission process, but this emission appears to be even weaker than this dissipation of the stellar wind in that I presented. So I just skipped the discussion about it.
It's even harder.
Yes, it would be even harder, but this is even more interesting because then this indicates existence of the moon. Not only the planet, but there must be a moon around the planet.
Okay. Okay, more questions? Łukasz?
Just a quick one. So time domain in the radios, do we expect any time variability here, or is it too low to be detected?
Well, depending what is the orbital period. I mean, once one day we detect such radio emission of the planet, then you have to follow to establish the orbital parameters, like in the optical infrared direct imaging of the planets. So the same story. So first you have to find such objects and then try to follow them. I mean, several times to observe to find the orbital parameters.
Yeah, this is excellent. This is a perfect case for us to investigate.
So if it's H1, in principle, you should see the transient.
Transit, you mean?
Yes,
transit.
I mean, if there is emission, you should see some eclipse of the planet by a star, because you must know that, for example, the magnetic field of the sun is about one Gauss, which is much weaker than the maybe not. Well, yes, I mean the Jupiter is stronger. I mean, when the sun is quiet, the Jupiter is stronger radio source than the sun. So the stars should eclipse. But in the case of the A-type stars, it may be different.
Okay, we should move on. It's interesting in the context of pilot optical and radio observations as well, because it shows some limitations of this study analysis. But now we have time for the second speaker, who is Erika Pakštiene from University of Vilnius. And Erika will tell us about the astroseismology benefits.
I'm here. I have to restart my computer, sorry.
So you can use my laptop, for example, if you.
You don't have.
Yeah, no.
Your slides died.
What? Can we change? Maya, are you ready with your presentation?
Yes.
Can you switch the talks? And Elika will restart the computer, right? It happens.
Zoom is very demanding for computers.
Okay, so
We'll just start the timer since
yeah, sure.
I have less time than.
Small change. Now we will have talk presented by Maja Jabłońska from University of Warsaw.
Yes.
And this is the first hands-on, let's say, session about Black Hole Dawn. Maja will introduce us the tool we are using for our research.
Okay, give me a second. And
Sure.
I will just share my. Okay, I think you have to. You can see that, but with the.
Yes.
Okay, I will just maximize that.
Yeah.
Do you have your camera on?
Yes.
Yes.
It's
No, you don't.
Oh, you cannot see that.
Camera is off. Well, I just wanted to show the speakers.
Okay, it would be all right to see this stripe of other slides because I don't want to prolong it. But
I think it's fine. It's fine. Yeah.
Okay, great.
Just please turn on your camera if you can.
Turn on or off?
On.
Oh, it's
off, I think.
Okay. Okay, yeah, it is on indeed.
Okay, so Maja,
Yes.
please go on.
I will, but okay. Okay, I got it. I should be visible now. Great. Hello everyone. And I want to give a friendly introduction to BHDOM, which stands for Black Hole Target Observation Manager, which we are developing. I am one of the lead programmers, so I am really happy to introduce you. And the plan is to first briefly say what's the tool actually for, then say something about the integration with other services, which are used for gathering data and other things. Then I will present you how target is a keyword in our system and what actually does it stand for. And then something about processing the data, since it's one of the most important features. So first things first, our system is built on top of Target Observation Manager framework developed by Las Cumbres Observatory. And we are developing it on top of that framework and adding our features and integrations. Then what's the tool for? It's, of course, for storing the data, which can be from many sources and in different formats. And this is very useful to have a unified way to store them. Then Black Hole Dawn is integrated with other services, which I will elaborate on later. Then, of course, we have a way of processing the data, such as calibration, and you can then download all the results. And another feature of the target observation managers in general is to plan the observations. So let's start with integrations with other services. If you search for targets, you can use existing catalogs. Of course, the one that is very interesting to us is Gaia Alerts, but not only, since you can also connect to transient name servers and other catalogs, this group of catalogs will, of course, be expanded, since that's the way of developing this BHDOM system. Then I will elaborate on that later, but we have added a unified way of name fetching, since the target can have many names in all these services, and this is a confusing thing, and it can really stand in the way of smoothly downloading the data. Then we also download the data from, for now it's 4 services, and it happens automatically. Of course, you are not limited to that since you can add your own data as long as they are in correct format. Now I would like to speak about the target, since I have mentioned that it is a keyword when it comes to BHSOM system, of course, because we are focused on observing the targets and following the brightness changes. So you have everything you need under the name of a target. Of course, the basic data such as coordinates or these catalog names I have mentioned that can be different in different catalogs. Of course, cadence and target importance and observing priority. These are things regarding the observations, and this will be elaborated upon in tomorrow's and Thursday's presentations. Sometimes the services also have some classifications of these, like preliminary ones. And the most important thing is, of course, the data. For now, I will speak about the photometric data, since this is something we are currently working the most on. First, I will just show you the user interface, which is, I believe it's simple. And I want to show you that you have all these basic dashboard features, such as latest targets sorted by last observation date, or yes, this is an extended view of all the targets, which you can sort by choosing columns. Probably the most interesting ones are the number of observations or observing priority. You can, of course, filter targets, so all the necessary dashboards functionalities are there. And there are 3 ways of adding the targets. The first one is to just manually fill the form in. So it is not limited to the catalogs I have shown, but the catalogs are the easiest way. You can, of course, import targets. Also, we can import that from other systems like BHSOM, since that's a simple CSV file. And yes, you can search these catalogs for a target, and all you have to do is to provide this correct name, for example, the Gaia internal name, and it will all be found for you. Then I would like to show you the target dashboard and the most important features of that. So, of course, you have all the basic information, such as the coordinates, which are all filled in when you search in a catalog, as well as the galactic coordinates. And now, these are the catalog names I have mentioned, and these are different for all the 4 catalogs we fetch the data from, since that's the this is where it's important to differentiate between these names. And you can automatically fetch these names from the catalogs such as Gaia, ZTF, and AAVSO. Calib server name is the internal CPCS name. I believe this will be elaborated upon tomorrow. And this fetching is done based on the coordinates, so you have nothing to worry about. As long as the names are somewhere in TNS or Simbat database, it will be fetched. And of course, you can fill that in manually in case of some very new targets where it is, for example, not being detected by ZTF. Yes, and now I would like to speak about the data, and most important are the reduced data, which are pre-processed by CPCS, so that's the calibration system that BHSOM is connected to. And all the data have the values of observer and facility, and of course filter magnitude and MGD. And this is how you can access all this data. You can see everything on the static plot. This is where you download the newest data from these 4 catalogs. As long as the names are filled in, since these are, this is something that the target is searched by. And this is why it's important to fetch these target names for all the catalogs you want to use. And the fetching from all these 4 catalogs is done automatically twice a day. But you can do it manually as well. This is a feature that is currently in development, but stay tuned, since we are about to add a microlensing model that is models to this target based on the existing observations. And this fancier interactive photometry plot, which can't be directly in this dashboard, since sometimes there's really a lot of data, and it just takes a while to render, but you can access that, and then you can see all the extra information, such as the owner or the facility, and of course do all the things such as scrolling and zooming in. And of course, it is very necessary to have this feature and to be able to download the photometric data in the most basic CSV for some further processing. Then you can, of course, upload your own data. Specifically, you can upload FITS files that will be reduced for you. You can also download some pre-processed data in the form of CSV. And also we have added an automatic reading for ACSN format, since it differs a little bit, but that's done for you. So all you have to do is to download, since this catalog doesn't have an API. Yes, we serve as supported data formats. And when providing the FITS file, how it is done under the mask. Sorry for referring to tomorrow all the time, but just in case you are curious, you will get this knowledge, just not today. But this data from FITS files is pre-processed for you. It's reduced. And you have to just provide your observer name. The filter is also determined for you, but you can force it. And you have to create an observatory. And today I am talking just about the target, so observatories are in the plan tomorrow or Thursday. And if everything is fine, then you should see this message. It might take several minutes, and it usually does. And then you can just check everything in the data tab. If something's not well, then you will know about it. I'm sorry for the incorrect number, since that's definitely not slide 11, but yes, it's 36 actually. And then we have the features to download the data to be ready to just paste into the publication you may be writing using this data. So this is the table that was generated for, I believe, Gaia 20 FNR. And you can also download this summary to include anywhere you want. And to sum everything up, I also want to do a sneak peek of the future features, since we are working on automated classification of these targets, and that will be connected, and you can get a hint what is this object. Of course, the microlensing modeling I have already mentioned. Of course, more integrated services, since this is something that TOMs are perfect for. You can just add all the services that have an API, or just any way of fetching automatically. And of course, the observation planning, which is also absolutely possible for the robotic telescopes and will be worked upon. And yes, I rushed a little bit since I was afraid I won't get it all in time. But if you have any questions or feedback, you can always contact us and write on Slack. And this URL is our system. You can test it out for yourself, and we will help if anything is needed. So thank you very much.
Thank you very much. Yeah, it was quick, actually, but it's fine.
I'm sorry, I was really
it's
afraid I won't do it in time, so I overdid that.
No, it was.
I would like to comment that I asked Maya to give this overview to everyone here almost at the very beginning of this meeting, so that then you know whom to ask about the details and what she can talk to you about, right? So this was kind of an introduction to the system and what Maya is responsible for which bits. And then we have the rest of the week to talk more about the details, right? So use the time and go to Maya and talk about these details.
Yes,
right?
and I will also happily take suggestions, because since I am developing these things, I can add something that you may need or you are working on.
That's right.
So I would be happy to talk about it and, of course, elaborate on anything or help. And once again, I'm really sorry for rushing. But my stopper turned off and I couldn't see the time.
It's better. We have a lot of time for questions and discussions. Yeah, as Łukasz said, it will be the Maya actually said as well. That was the first presentation about Black Hole Dome, the introductory one. Tomorrow we'll have a session, the presentation prepared by me. So I will also show you some details of how to use Black Hole Dome and other tools from the user point of view. And the day after tomorrow, Przemek Mikołajczyk will present you the engine of Black Hole Dome and the main tool which we based on when processing the fixed images. Because as you already know, Black Hole Dome can process fixed files automatically. Okay, it's time for questions. So I see the question from Haro Verkauter. Please, you can ask your questions actually.
Okay, so you mentioned that you can upload FITS files.
Yes, yes.
But FITS files, FITS is just a standard for how data can be stored on disk. It doesn't say anything about what's in the FITS file. So we can, with our software, with the data reduction, we can produce fixed images as output. So if we upload, is there any idea that if we upload them, that they will be handled?
Well, yes, actually you can upload any FITS files, and yes, you need to do it in the correct targets for it to process and produce a point that actually. Sorry, I don't know where to look actually when answering the question. But as you, okay, maybe I didn't full screenshots, but yes, you are uploading regarding the information such as facility name, observatory, and targets that can or that doesn't have to be in the FITS file. So this is something that is handled in the user interface of BH-TOM. So this is, you have to upload the FITS file to the correct target and write all the information you want to be included in the data point in this form. And when it comes to incorrect FITS files, you will just get an error message if it is incorrect indeed. So yes, if all's fine, then then we will just see the success message, and also the point will appear. If it isn't, then you will get an error.
No, if I may barge into the discussion, because I'm the person responsible for the photometric processing, and what I understand you asking saying that feeds can store anything, that spectra and let's say light data.
Well, actually, the visibility data, the Fourier plane data, also.
Sure, yeah, you can store anything, but what we maybe can go back to the list of possible
formats.
Formats, yes. Here we state that it fits. Maybe
oh yes, fits for photometric processing.
And the first step, which is taken after you upload the fixed file, it's being checked with our database if your instrument has been registered in our database. So if you upload something that it's not listed in our database, you will just get an error message, and maybe in the future we will work on the messages to be more clear, like your observatory doesn't exist, or this is not a proper image of the skies.
No, but for example, the units that we use in our image in radio are not magnitudes, they will be something different. So that's immediately probably something that the software will fail.
Sure. That's why we require all the observatories to provide, let's say, for example, gain of the XCD camera, so we can do the proper flags, photon flags transformation. So all the observatories have the same units in magnitudes. These Nyanskis or
but we don't have CCDs. So.
Exactly. So it's not possible for now, but that's a point for the
we have to go down to the very low level.
Yeah. But so, and that is one reason for my comment was, well, can you specify fits files? But that may be a bit too generic.
Yeah.
It's something to keep in mind.
Yes, so this is why it's great to have that discussion, because this is all something that we can include.
And I'm pretty sure if the backend can make decisions based on the keywords in fits file, then we can branch off and do something different.
And for now it works exactly like that. So we read the keywords, and then we kind of know how to what steps should we take next.
Okay, so probably that is the way to go
forward. Yeah. Exactly.
Okay. Good.
Thank you for that.
Okay, the next question from Siegfried van Averbekke. So does it do binary lens modeling if necessary?
I'll cut it out here because we've discussed it already on the chat.
Okay, you move it to the chat.
Okay.
Well, we should move it to Slack actually, so that more people can see it.
We
responded
to Slack,
to the questions already.
Okay.
In the chat.
Okay.
Okay, great. So I guess we are short on time, so it's perfect way to end, and we can.
So Łukasz, you answered for all of the questions, or?
I think so. If someone feels their question is not answered, then please post it again in our Slack channel.
Yeah, there is a Slack channel.
Hello.
Yeah.
Hi, this is Josh Hamsch from Belgium.
Hi, Josh.
Hi, Josh.
I had raised my hand. Since Maya has chosen as an example Gaia 20 FNR, I wonder whether you have downloaded all data from the AVSO, because I miss the B band channel, which was not on the pictures she showed.
I think we do have B.
Yeah, B was from APAS.
It was on APAS, you're right. We will double check. If there is extra B data, B band data, we should also upload it, yes.
Yeah, B band, and I mean, I have BVI band data I will show on Thursday.
Okay, cool.
Okay, thank you. There is a Slack channel dedicated to Black Hole DOM as well, for Black Hole DOM users. So you can contact us by using a mail address presented by Maya, but also by using Slack channel. But you can also write on the Slack of this workshop.
Okay, thank you.
Yeah, thank you very much. So now we can continue with Erika's presentation. You should see this presentation already on your screens. It will be about the asteroseismology. And Erika, are you ready?
Yes.
So please go ahead.
Yes. Hello, everyone. I'm Erika Pakštienė from Vilnius University, and I will talk about asteroseismology. We use for analysis of stars to characterize them and to characterize exoplanets too. And I will talk mostly about solar type oscillations because actually they are very useful. And we have found many solar type oscillators in a test continuous viewing zone. So recently, in recent decades, we have more and more opportunities to use asteroseismology as powerful tool for analysis of the stars to derive their parameters, structures, and evolution over HR diagram. Also, they may be used for characterization of companion stars in binary systems or exoplanets if those variable stars are hosts of exoplanets. Yes, thanks to space telescopes, which most of them are dedicated to search for exoplanets, and which requires the same methodology for observations of light curves as asteroseismology. We can share those instruments and get good light curves for asteroseismology. Good light curve for asteroseismology and exoplanetary science should be as long as possible and observed with as short sampling time as possible to get more precise data, less noise in light curves, and get better precision. And also it allows to find small amplitude pulsations, which we couldn't observe from ground-based observatories. So we have many space telescopes, and all of them observe different types of light curves. For example, Gaia can observe long light curves, but the cadence is very long. Such telescopes as most bright Crete observed with sub-millimeter cadence, but light curves were quite short. Kepler telescope observed very long light curves, but it had limited storage on board and couldn't store full frames of observed sky. So it produced only light curves for a certain number of targets. Most of them were observed with 30-minute sampling time, and only 512 stars per quarter was observed with 1 minute sampling time. But Kepler observations have shown that short cadence is very important for asteroseismology and to get precise results. And now we have a test which was launched in 2018. This is different telescope, much smaller. It has 4 small lenses and scan full sky. So here on the right, you can see the sky map. Different colors correspond to different sectors observed by test. And around the ecliptic pole in the north and in the south, we have a region which we call continuous viewing zone, which was observed for 1 year continuously. And TESS has a big storage, so it stores full frames of all these sectors. So all stars from the field may be analyzed. Yeah, and during the first 2 years, TESS observed stars using 60 minutes cadence and stored full field frames with such cadence, but also it produced 2 minutes cadence light curves for 20,000 preselected stars. Now we have extended TESS mission, and now TESS observe even with shorter cadence time. So it stores full frames images with 10 minutes cadence and produce light curves for preselected stars with 20 seconds cadence. Yes, short cadences provide new opportunities for astroseismology and for exoplanetary transit science. We have shown in one of our recent papers that TESS 20-second light curves give from 10 until 25% better precision than 2-minute light curves for stars brighter than 8 magnitude. And the precision for both light curves gets the same when the magnitude of the star is around 13 magnitude. Yes, and here is an example of power spectra for 3 different bright stars with solar-type pulsators and small amplitude pulsators. The upper panel blue curve corresponds to power spectra calculated from light curve with 2 minutes cadence, and on the bottom is power spectrum calculated from light curve with 20 seconds cadence. So you can see that some pulsations in the upper panel cannot be recognized at all. Yeah, let's go to the continuous viewing zone. Our astronomers from Vilnius University, together with Aarhus University, decided to characterize stars from continuous viewing zone in the northern sky. We selected bright stars which are brighter than 8 magnitude and with temperature smaller than 6,500 kelvins. And performed a high-resolution spectroscopy for all of those stars. In the beginning, we had selected 302 stars, but later the number reduced the number to 277 because not all stars were suitable for spectroscopic analysis. So we did the spectroscopy with 1.65 meters and high-resolution spectrograph, Eshel spectrograph at Molėtai Astronomical Observatory in Lithuania, and derived spectroscopic parameters for 277 stars. At the same time, we analyzed light curves for all of those stars downloaded from TESS archive, and found 90 stars with solar-type pulsators among those 277. And here is shown a morphology of those stars. The blue bars corresponds to full set and the magenta to solar-like stars. So when we are looking for solar-like pulsators, what we expect to see in their power spectra. So here are examples of several red giants with solar-type pulsations. So we can see low noise at low frequencies here, which appear because of turbulence in the upper layer of the star. And here, more to the right, at high frequencies, we see solar-type pulsators. They appear at a different frequency, and this frequency of maximum power depends on log G of the star and also on the temperature. But this is more sensitive on log G, so we can say that the smaller log G is, the smaller pulsation frequency appear here in our spectrum. If we zoom in this group of peaks of solar pulsations, we can see here some equal spacing between modes. And we are mostly interested to determine the spacing between radial modes, L equals 0, which is shown here. Also here we can see small separation between neighboring modes like L equals 0 and L equals 2, which also may be used later for determining some parameters of the star. And if we cut this spectrum into the pieces, and the length of each piece should correspond to the large separation here between radial modes, and put those pieces each on top of other, we can get the Eshel diagram, which is shown here. On the right side, you can see the Eshel diagram for the sun. On x-axis, we have frequency modulo, which is equal to large separation, and on the y-axis, we have cycle frequency. And on the right side, you can see another Eshel diagram, which is plotted as color map for red giants, and here we cannot find the mode L equals 3, which should be somewhere here, but it is missing. Probably the amplitude is too low. So when we have determined large separation, small separation, frequency at power maximum, when we have determined the spectroscopic effective temperature, we can use scaling relation to determine the mass and radius of the star. And also there is possible to calculate the age of the star. Of course, these relations are slightly different for different types of solar pulsators. So the upper two frequencies, they were proposed around 20 years ago, but they are still in use. But some scientists trying to get more precise equations, relations. As an example is given here. 3 equations, relations proposed by Bellinger in 2019, which fit well main sequence solar pulsators. So when we can use those scaling relations, but also if we want to get more precise data, we use stellar modeling, we model individual frequencies and get more precise parameters of those stars and also stellar interior. We have determined mass, radius, and age for our 90 solar type pulsators, which are red giants. You can see them here on HR diagram. There is no solar type pulsators close to the main sequence because sampling time of the light curves was too long to detect high frequency pulsations in those stars. So we cannot say about those stars anything. And now I'll talk a little bit how we can use astroseismology for planetary science. As an example, well, the problem is that we have very few planets which are well characterized and are flying around variable star. This plot shows all those stars. Most of those stars with transiting exoplanets were observed by Kepler, which shown here. All those stars are quite faint, and we cannot do precise astroseismology for them, especially if those stars are solar type. Here is one system, P-Man, around the star P-Man, which is solar type pulsator, and has two exoplanets. One of those exoplanets is transiting, another one was found before the TESS mission by radial velocities and has big eccentricity. So here you can see that system. Transiting planet is this one. P-Man C, and P-Man B has eccentric orbit here. And probably you know the problem which calls Fulton gap or planet radius valley. There is a lack of planets with certain radius around 1.8 between subneptunian planets and super S. The problem is that we don't know why there are less number of those exoplanets. We need to find more stars which are in that gap, and that probably will explain us, okay, what is going there. So we did analysis of parent star, P-Man, using astroseismology. Several groups used different methods, and we found some compromise. We derive parameters for that star, derive parameters for exoplanet P-Man C, and put those new parameters into the radius period diagram here. So P-Man C planet appear at the very edge of the gap, at the upper edge of the gap, and this rectangular shows the previous results from other works. So we see that this, according to other analysis, it is at the very edge of this gap, and that means that this is subneptunian planet with quite thick atmosphere, and probably it will evolve quite quickly through this gap to the super S. And probably I will stop at this place. If you are interested in this work, you can find more information about methods used for the analysis in our paper, which was published this year. So, thank you.
Thank you very much. Thank you, Erika, for your interesting talk. Any questions? Please raise your hands on Zoom. I don't see any hands. I have one short question. It's a quite interesting case, this two planets around this system, because the orbits are not coplanar, right?
Yes, yeah.
And what could be the reason of this?
I think probably that was an influence of another object, and it moved from original orbit a little bit further. Or that could be that some planet drifted closer to the star, and its gravity pushed that planet to another orbit. So that was some interaction between objects.
Okay, I see. Thank you very much again. Thanks to all of you and the presenters. Now we will have a talk which will be connected also with the seminar in the Warsaw University Astronomical Observatory. Łukasz is going to host this seminar and this talk. Yeah.
Let me explain that we will need to switch to a different Zoom. So please find the link I sent you this morning, and then there you will have the different Zoom link for the special seminar of today, which will be also transmitted in Warsaw, in Crete, from Baltimore. So see you in 10 minutes on a different Zoom.
Okay, that's all from my side. Thank you for your participation.